That's not even fair.
Yeah, no, it's not fair.
You see, players shit on players every day.
Bro, yeah, your friend. Yeah, I've got to get six and then you get it.
Your player with the console card, he'll handicap your entire team.
Because you might do it. You woke up at like 2 and they didn't even say
No, are you sure?
And did you hear about the apparently it's that the Xbox and PlayStation first.
Square root gives you 1.3 times 10 to the minus 3, and the negative log of that is not a half, it's a square root. I don't know why do you use a half? No, plus is the log. We're going to get to that. This is definitely correct because, in fact, we will discuss this in a moment. This is the correct. Half. All right. So let's just like reflect on this, guys. So basically, what have I done here, right? This is how I deal with the weak acid. That's the Ka value. Multiply that by the concentration, square root it, get the concentration of H3O plus.
Can you go back to the last slide for 1 second, please? Okay, so right there. What do you do to get to the next step? That's
okay, so we know that the concentration of these two guys is the same because of the stoichiometry. So instead of we can call that X, we can call it whatever we want to. It's going to be that times that. Those two numbers are the same. We're trying to find that number. It's going to be something squared. I just called it H3O plus squared. We know Ka, it's 1.7 times 10 to the minus 5. So, and we know what this guy is. This is the initial concentration at 0.1. So we basically plug in the values. We get that. H3O plus squared. Why squared? Because these two have exactly the same concentration. And they have the same concentration because it's a 1-to-1-to-1-to-1 reaction.
Yeah, and then
right. Then you square root it, and you solve for H3O plus, and you take the negative log of that guy there, and you get 2.8. Now, somewhere in this whole calculation, I've sort of done something. What have I done? I've made a sort of an assumption. The assumption I've made is that the concentration of the acetic acid is 0.1. See? That's the concentration of the acetic acid solution, and I plug that value into this expression. Is that correct, strictly speaking? No. It's going to be slightly less than 0.1, because some of it's going to dissociate. So in fact, if you want to do this correctly, what you've got to do is you've got to do the following. Okay, let's just call this x squared. You've actually got to take that into consideration in that way and solve for x. Because some of it is going to, the concentration is not really going to be 0.1, it's going to be 0.1 minus x, because some of it's dissociating. Now it turns out, and you can do this as a homework exercise, if you solve for x there, which will then give you basically the pH, you will see that the value is about 2.88 as well. Now why is that? The reason for that is that the dissociation is so minuscule, because it's a weak acid, that the concentration is essentially unchanged by the dissociation of the acetic acid. The reason why we do this is for convenience, right? Because if you solve it that way, which is, let's say, the more correct way, you end up with a quadratic equation, and you have to use the quadratic formula to solve it, which is cumbersome. And the number you get at the end is anyway approximately the same. So this is an approximation. The approximation is that the concentration of the acetic acid is going to be approximately the same as the initial concentration. The slightly lower concentration of the acetic acid due to the dissociation is negligible. But that would be the correct way of solving it. So you guys can try this at home. You can now do things the other way around. If I give you the pH of the acetic acid, I can say what's the concentration of the solution, and then you basically do everything in reverse. You plug in the, so here we have the pH, you find from the pH the H3O plus value, square it, you have Ka, and you'd solve for the concentration. So you must be able to do this sort of, if you have the concentration, find the pH, or if you have the pH, find the concentration. So that's how we deal with weak acids. Okay, now let's continue. The third model, yes?
Is there anything in between a strong and a weak thing?
That's a very good question. That's a question a student asks every year. And the answer is yes. The question is, at what point will this assumption break down? That's basically what you're saying. At what point will it not be weak enough that if I don't take that minus x into consideration, well, sort of the rule of thumb is, let's go to the table, actually, and look at some values. The rule of thumb is if you have something like this, that's 25, that's a pretty weak, that's considered, let's say, a kind of a, well, that's a strong acid, but if 25, you'd have to sort of take it into consideration, certainly. But if you start getting into this regime here, where you get even 10 to the minus 1, then you can actually make that assumption. You can actually test this. You can actually see at what point does that assumption break down, where I can just take the minus x out like I've done it. It's a good question.
Okay.
So obviously, the weaker the acid, the more appropriate is it to use this assumption that I have, that you can just neglect the minus x.
Okay.
But yeah, for this course, if it's a weak acid, you can use the assumption. In other words, you don't have to solve it this way.
Right.
Okay? Right. So we've now looked at Lowry-Bronsted, we've looked at Arrhenius. There's a third and very important model of acids and bases called the Lewis model. You've encountered this guy before. He was, in fact, a bit of trivia, nominated for 41 times for a Nobel Prize and never won it. Right? Lewis, of course, is the guy that came up with drawing Lewis structures, very important in understanding valence bond theory. And, of course, you all know him already. But he came up with a third model, because it turns out that the Lowry-Bronsted model of acids and bases also has limitations. And there's some substances that behave as acids and bases that you cannot explain in terms of acids being donated or transferred, okay? And for that we need a third model called the Lewis model, which is based on electron pair transfer, okay? So this is just what I've said. The Lowry-Bronsted model is based on exchange of protons, and it's useful in aqueous media. Similar reactions exist without exchange of H pluses. And this is very important, in fact, in inorganic and organic chemistry. And more advanced and sophisticated chemistry, you very rarely, it turns out, work with Lowry-Bronsted or Arrhenius. This is the model that becomes very, very important in later chemistry. Okay, very important. So I just want to introduce you to this. This model is based on electron pairs being accepted or donated. So a Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. So now we're defining acidity in terms of donation or acceptance of an electron pair. Here's an example. This is boron trifluoride. Remember, you've encountered this before. If you draw the Lewis structure, it's an exception to the octet. Remember, it only has 6 valence electrons. So I said in the lecture, actually, it's got this free p orbital, and it's hungry for electrons. So if you expose it to something that has a lone pair, like ammonia, the ammonia is going to attack it and you're going to form basically an adduct that we call a Lewis acid base adduct. Okay, that's what happens if you expose boron trifluoride to ammonia. Now in this case, the boron trifluoride is acting as a Lewis acid because it's accepting an electron pair from the ammonia, which is behaving as a Lewis base, and we use an arrow to denote the movement of the electron pair. And this arrow pushing, some of you might know from organic chemistry, is very important. This is another example. This is calcium oxide. There you have a reaction between calcium oxide and sulfur dioxide to form this here. Notice you can't explain either of these two reactions in terms of protons being shuttled around. So that's why this is behaving in this case as a Lewis base, because it's donating its electron pair from the oxygen, its lone pair, to the sulfur dioxide. The sulfur dioxide is behaving as a Lewis acid. So this is a whole different model. Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. And again, very important in organic chemistry, yes.
So, when you're actually writing out the equation, you would write it like that, or roughly like that.
Correct.
Not like SO2 as opposed to the S and things.
Well, I mean, of course you could write SO2, but this is just, it just enables you to sort of show what's going on and how the electrons are moving around.
Okay.
So Lewis acidity and basicity is very important, okay? But this is the third model. So then now we've looked at all three models. Arrhenius, which is sort of the first one, then Lowry Bronsted, and then Lewis. So you see, this is again a nice example of how science works. We start with something simple, it breaks down, we come up with something better, it doesn't work anymore, and then we come up with a third model. And by the way, most acids, or some acids, you can describe in terms of all three models, okay? Right, so here are some properties. Lewis acids tend to be cations, they tend to be metal halides that have incomplete octets, and Lewis bases tend to be compounds with lone pairs on them, obviously, because per definition, a Lewis base is an electron pair donor. So again, Lewis acid, electron pair acceptor, Lewis base is an electron pair donor. Okay. So this is the take-home message. An acid, according to Arrhenius, according to Lowry Bronsted, is a proton donor, a base is a proton acceptor. According to Lewis, it's an electron pair acceptor, an acid, a base is an electron pair donor. So you see that these theories are sometimes complementary but different. And we define them differently because some examples exist that don't really fit into the model that we've described. How do we measure pH? This is now the next thing. Well, we can use a pH meter or we can use indicators. What are indicators? Indicators tend to be organic substances, right? Carbon-containing substances that at different pHs react differently and get different chemical structures that have different colors, okay? And this is a very nice example. We used to do this in Berlin. If you take red cabbage and you boil it, right? And you extract the red cabbage out of it, it makes a beautiful indicator. So this is what basically using red cabbage as an indicator for different pHs looks like. You can see here going from a basic pH through to an acidic pH. They have different colors in each. It's kind of like a universal indicator. So that's something fun that you could try at home over the Christmas holidays and impress your relatives. Okay, so that's pretty cool. And the reason why that happens is because at different pHs, there's of course different concentrations, as we've just seen, of H pluses, which then interact to a greater or lesser extent with these organic compounds in the cabbage and then change their color. That's how an indicator works. So we're going to come back to indicators in a second, but I want to talk now about something that's extremely, extremely important, and you've encountered this hopefully already in the pre-discussion of the task, and that is this notion of buffers. What is a buffer? Well, a buffer is a system that resists pH change, right? Why are buffers important? Well, if buffers didn't exist, there would be no life. It's that simple. Because if you didn't have buffers in your body, and you took a sip of Coca-Cola, which is pretty acidic, and you didn't have buffers to regulate the pH change, your pH would drop immediately, your proteins would start to denature, and that would be the end of you. Buffers regulate pH change, and they're very important in biological systems. And what is a buffer? Well, a buffer is typically, in the classic case, it is typically composed of a weak acid and its conjugate base as a salt. Now here we have a buffer system that is composed of acetic acid and its conjugate base, which is the acetate ion. Now what that basically means is if you want to make a buffer of the system, you take acetic acid, which is essentially what you find in vinegar, and you put something like this into it. That is the salt form of the conjugate base. For example, sodium acetate. So this is now the CH3COO minus is the conjugate base of this guy here, according to Laurie Bronsted. And you can get that as a salt. Sodium acetate, lithium acetate, magnesium acetate. So this is a salt that you have in a bottle, right? And you put the two together in a certain ratio. We'll see how you figure that ratio out in a minute. And the combination of these two is, this is an example of a buffer. So you typically in a buffer have a weak acid, typically, a weak acid and its conjugate base as a salt. Right, so you throw the two together, you mix them up, and you have a system that resists pH change. And basically how it works is this is the buffer system represented schematically here. If I add a base, what basically happens is the base, the OH minus, will react with the acid and get neutralized. So it resists the pH change. And if I throw in an acid, the acid will react with a conjugate base, which is present as a salt. It will get neutralized. So it basically eliminates changes in pH. Now, that doesn't mean that you can drink sulfuric acid. Buffers have a limited so-called buffer capacity, right? And you can actually calculate that. But basically, this is very important in biology. Okay, in the classic case is acetic acid, sodium acetate. So this is what I've just said. You typically in a buffer have a weak acid and its conjugate base, and its conjugate base means its conjugate base as a salt, which you can actually, you have this stuff in a bottle, sodium acetate. That's a salt in a bottle that you can actually add to the acetic acid. So you can also make buffers, which is much less typical, but it's possible, a weak base and its conjugate acid as a salt. For example, ammonia and ammonium chloride. Okay, would be an example of a buffer system where you have a pretty weak base, ammonia, and its conjugate acid, which is ammonium chloride, as a salt. You see, it's as a salt. So the very important equation that we have to deal with buffers is the so-called Henderson-Hasselbalch equation. This is very important. This equation enables us to, if we have a buffer system and we know the concentrations of the acid and its conjugate base, to determine the pH of the buffer system overall. Let's go through the derivation of this equation. Let's start off with the acid dissociation of a weak acid. There we have it. HA plus H2O forms A minus plus H3O plus. You've seen this before. That's the Ka expression for, we're now just keeping it generic. Let's just call it HA. So this is just for any weak acid, for any acid in fact. That's the Ka value. If I rewrite that expression, I just take the H3O out of the bracket, I get this expression here. It's basically, we're just doing some mathematical tricks, right? I just factor this out. And if I now take the negative log of both sides of this guy here, so negative log of both sides of this expression, I get this here. Does everyone follow that step? We're deriving this important equation, right? Because negative log AB, or log A B is log A plus log B, right? Log expansion. So all I've done to get from this step here to this step here is I've just taken the negative log of both sides and I end up with that there, right? Now what is negative log Ka per definition?
PK.
Correct. And what is negative log H3O plus? pH, right. So I get that expression there, and if I rearrange it, I get that expression there. That's the derivation, a very simple derivation of the so-called Henderson-Hasselbalch equation. It enables me, if I know the pKa of the weak acid, or the weak base, whatever I'm working with, in the buffer system, and I know the concentration of the conjugate base, A minus, and the concentration of the acid, HA, to actually calculate the pH of the buffer system. Right? And there it is. So that's the equation. Very simple, but very important. And I expect you to be able to derive this equation, because I don't like people memorizing equations. This is something you can derive yourself, and yeah, it's nice to have an equation named after you, especially when the derivation is so straightforward. Okay, now let's think about this. Let's suppose I am a scientist, and I want to make a buffer system for, let's say I go to the Antarctic and I find some microorganism that I discover thrives in a pH of 3.5. Okay, so I take this microorganism back to my laboratory, and I want to now make, of course, a buffer to grow the thing. I want to grow more of these, let's say, bacteria, and for that I need a specific buffer. So I can use the Henderson-Hasselbalch equation now very elegantly to find out what I should use to make that buffer system. How would I do that? You're a scientist in a lab. You want a buffer that's 3.5 so that you can grow in a petri dish, let's say, this new organism that you've discovered thrives in a pH of 3.5. Why do you need a buffer? Because the microorganism is going to be producing waste products, which if you just throw it in some water, is going to, of course, change the pH, and then the microorganism might cease to grow. So it needs to be